So logistics-wise, you can still have a cheat sheet like the other two exams, whatever you want on one side of a sheet of paper. The exam will be similar as far as point distribution. I try to do it equally across all three chapters, 25, 28, and 29 in this case. And it will be a mix of multiple choice and calculation, about one third multiple choice as far as points go, and two-thirds calculation. So, chapter 25, capacitance. A big conceptual idea that I've tried to hammer home, but is kind of a confusing one, is capacitance does not depend on charge or voltage, it just relates the two. And so if you put a certain charge across or onto the plates of a capacitor and measure the voltage across it, you divide those two, you will get a number. And so we call that the capacitance, but it doesn't depend on the charge or voltage. What do I mean? Well, if you double the charge, the voltage also doubles. And so that ratio of the two is still going to be the same number, even after changing how much charge is on the plates. The only way you can change that number C is to change the plates themselves or put a dielectric in between them. The idea of dielectrics is to increase the capacitance, and the main kind of questions you can expect about them are either just to calculate capacitance, given some information about the capacitor, like the plate area or spacing, or it could be some variant where I give you capacitance and I ask you to calculate the plate spacing or some other variant. So it could be a lot of different things, but it just depends on this formula and then how capacitance relates to charge and voltage. So this formula, just lots of variants of that type of question. Concept-wise, these questions, and there was one that was similar on the quiz. This is about the only two types of questions that can be asked as far as dielectrics go. And the only variants that can really happen are whether you add in a dielectric or remove a dielectric, but the trends are still the same. You still can use the analogy of the water tower, say, by adding a dielectric, I'm making the water tower bigger. By removing it, I'm making it smaller. If we're saying that the capacitor is still connected to the battery, then voltage is fixed. If we're saying that the capacitor is disconnected from the battery, then charge is fixed. And then you just reason out, well, if the water tower is getting bigger slash smaller and the either amount of water, which is the charge, or the height of the water, which is the voltage, is fixed, what happens to the other quantity? Or you can just do the math version of it, which is quicker, but I think it's easier to have things go wrong with that. You can expect one like this. So I would ask you what is the equivalent capacitance, and then maybe how much charge is on a particular capacitor. And so it's the same thing as with series and parallel resistors. The only difference is the role of series and parallel sort of swaps. If you have capacitors in series, you do the 1 over stuff. If you have them in parallel, you add. Otherwise, it's the same procedure as with resistors, and you basically just start with your original circuit, simplify down 2 capacitors at a time, and then once you've done that, work your way back up. Find everything there is to know about the circuit, the simplest possible circuit, this one down here, and then work your way back up. Once you know everything about that, you can propagate some of that information back to the more complicated circuit, find some more details about it, propagate that back to the original circuit, find details about it. So it's sort of working your way down and then all the way back up. If there were something about energy stored, it would just be combined with a question like this. So, for instance, how much energy is stored in capacitor 2 in this problem? Well, once you find either the charge or the voltage across that capacitor, you can answer that with one of these 3 equations. Depending on what you know, either charge or voltage, one might be more convenient than another. But just like with resistors, if you're going to use this equation, or any of these equations, you have to specifically know the charge across the capacitor you're looking at, the voltage across the capacitor you're looking at, not any old voltage, any old charge. So you got to be a little bit careful with those. RC circuits, um, I don't tend to get into the stuff where you have to use natural logarithms on exams, so I would say primarily conceptual type questions for RC, meaning stuff about these sort of trends, and same for charging. And then just how much charge is stored at the end, or how long does it take to fully charge up, which remember it's 5 time constants for it to charge up fully, also 5 time constants for it to fully discharge. Um, so, I mean, this example pretty much covers just about all of that. I guess it doesn't have how much charge is stored because I think we did that in an earlier version of this problem, but it's just whatever the battery voltage is, V0, multiply it by the capacitance. That'll tell you how much charge you've got stored on your capacitor at the end of the charging cycle. All right, chapter 28. The main concept stuff is all about the right-hand rule, the first right-hand rule. So you can use whatever version of it you want. The questions aren't like which way should your thumb face for the right-hand rule, so it doesn't depend on which version of it you use. The only thing that matters is I give you some information about, for instance, which way a charge is moving and which way the field is pointing, what's the direction of the force on that charge. The usual trick that I can pull is if it's a negative charge, you got to remember to flip the force at the very end of this process. So if you have a negative charge, it is opposite the direction that the right-hand rule, at least at first pass, is going to tell you. Calculation-wise, you can see things like that show up. What is the radius of the circular path? In combination with this conservation of energy stuff, which is old stuff from a previous exam, but it can show up in combination with that. And then just the size of the magnetic force. So really for chapter 28, the math is very easy. The concepts are the hard part and what will get you on this chapter. So really study the right-hand rule. Hall effect, we kind of talked about with that. You got to look at what the electrons are doing, because otherwise you'll get the wrong answer for the direction of the Hall effect voltage. The idea with Hall effect is if you track the electrons, use your usual right-hand rule to figure out the direction of the force on them. Whichever way they move, you're going to leave positive charge on the other side. So like here. And that'll let you determine the polarity of the Hall voltage, or another way to phrase that is which side of the wire is positive, which is how I worded it on the quiz. Maybe you have to calculate it, but if you do, it's going to be a very plug and chug sort of thing. Not really any tricks with that. Same goes for the force on a wire. It's still the usual right-hand rule, and you just use a slightly different equation for it compared to a single moving charge. It actually is the same equation, just rewritten for a current, but if you're looking at a bunch of charge moving through a wire, you'll want to use this version. Torque. I could ask you which way the coil would rotate in a given magnetic field. So I'm saying if I gave you a picture like this, maybe I swap the direction current's flowing or something like that. Can you figure out which way the coil will rotate, clockwise or counterclockwise? All you have to do to be able to do that is use the right-hand rule on either side. So you could talk about it in terms of the normal to the loop, wanting to realign with the magnetic field. To me, that's a more confusing way to do it. Just do your right-hand rule, you'll be able to tell which way each side is going to get pulled, and that'll tell you, think of it like a steering wheel. If you pulled like that on both sides of a steering wheel, what will it do? In this picture, turn clockwise. Calculation, literally just that equation, very plug and chug. So I'd say if you're looking for calculation type examples, that's a good one. Okay, 29. You don't need to know the original Biot-Savart stuff. You do need to know second right-hand rule very well, because that's going to be the gotcha for this chapter, is if you get that wrong, you lose a lot of points because it's conceptual, and that means it's all or none. The main thing that gets messed up with the second right-hand rule is forgetting this third step. So you may say the field circles clockwise or counterclockwise around a wire, but if I need to know the field at a particular location, I got to think about what's tangent to that circle. So that's why I drew these arrows. At each of those points, the tangent direction is just, I picture something circling around and around in the direction I decided the field should wrap. So in this picture, it looks like it's wrapping counterclockwise. Well, if I want to know the field at this point, which way is my pin about to go? If I've been circling like that, it's about to go upward. All right, if I want to know the field at this point, which way is my pin about to go? Downward, so on and so forth. If you want to bring a roll of tape to help with some of that stuff, you are free to do so. It may be more useful when talking about the field created by a coil, though. You don't need this. You don't need all the derivation stuff. It's just calculation and direction of magnetic fields. This is combining the first and second right-hand rules. I could ask about that. Will the two wires attract or repel? If so, how much force acts on either one? So the direction's the hard part. The calculation is the easy part. Same here. I'll stick to full loops of wire. So no arcs, just full loops of wire or coils of wire on the exam. Difference between loops and coils is just how many turns you have. If I wanted the magnetic field due to a coil, I just take this answer and multiply by the number of loops, if I'm talking about right at the center of the coil. If I'm not talking about the center, it's this nastier formula, but you can see that if z equals 0, that one actually simplifies to this one up here. So this is a good example problem for second right-hand rule, as is this. And for calculation, you can expect like a problem where I've got a straight wire and a coil, or a straight wire and a solenoid, or a solenoid and a coil, so on and so forth, and I ask for the net magnetic field. And to get that, you'll use your second right-hand rule to figure out whether stuff is pointing up, down, left, right, whatever else. And then it's kind of plug and chug of the individual formulas for each of those fields. Ampere's law. Yeah, I won't put Ampere's law on there. Sorry, I don't want to scratch out solenoid. Just the Ampere's law stuff. I will not put that on there because we just use it once. It's not as heavy-handed as Gauss's law was, so I'm not planning to test on that. But for a solenoid, you have a formula to calculate field strength. If you want direction, it is still the second right-hand rule. But now you just have to be a little bit careful to think about, well, for any one loop in the solenoid, that's what I'm using as my current or the direction my thumb points. So in this picture, I see that it's sort of wrapping around like that. If I decided to put my hand on this loop, my thumb would go there, and I would try and grab onto the loop, which I don't know that I want to attempt to draw. Let's see if we can do something. All right. Could have gone worse, could have gone better. Grabbing onto the loop, something like that, and so my fingers dip through it to the left. That's where the roll of tape thing really helps you get it right, and you don't have to imagine doing it, you actually physically have something to do that with. Okay, so all this calculation stuff you do not need, you just need the final result and then the second right-hand rule to figure out the direction of the field. So, problem like that. I think that's my recap. Questions on anything?
For the solenoid, how would you deal with a question if on where it's on the exam, if it's regarding to like looking, if your eye is looking through a solenoid, if you're trying to like determine what direction or using the second hand.
So for that, it's just sort of picturing yourself in that perspective. So for instance, in this picture, if I asked you what would the field look like looking straight at it. That's your point of view. If you were standing over there looking down the barrel of the solenoid, you would see those field lines poking out at you. So, from your perspective, you would see all the loops of the solenoid, and you would see a bunch of field lines poking out. For poking out, we use the dot. So, this is how I would interpret if you're on that side, what you would see. If you're on the other side, you would see the field lines going away from you. So you would draw X's from that side. And so in that sense, it's you still use the second right-hand rule the same way to figure out the absolute direction of the magnetic field, but then that direction relative to you can change depending on where you're looking at that field from. Or if you're looking down at the top, depending on which way you're facing looking down at the top, you could be seeing the field point left to right or right to left. Um, I probably wouldn't do something like that because that's more ambiguous, but that's the idea.
I had a question.
Yep.
Uh, for the practice exam, number 11.
Okay. Yes.
Yeah, yeah. So my question is, I guess it's a more difficult way of doing it, but if you were to go back to the original circuit, how you talked about at the beginning of the stream,
Mm-hmm.
if you were to work backwards and try to find the charge individually on each capacitor, would that not be the total charge within the circuit? For all three capacitors right there, if you, I guess, summed up all the charge each capacitor has, should it not be the same charge as like the equivalent capacitance charge? Does that make sense?
Um, let's see. So if you've got charge that's leaving the battery, you'll have some go this way, some go this way, and then off of each plate, you have some come off and go onto that one. So I would say yes, the total charge leaving the battery is what sort of ends up on the capacitors. So that should work, but think of the parallel question for resistors, which would be I want to find the total current flowing from the battery through the circuit. I could do that by saying, well, current flows through this branch, if I'm pretending these are resistors for a second, and current flows through this branch, and then that current's going to flow through this branch, so I can add up what goes here, and that's what's coming from the battery. But I also know if I just replace all of these capacitors with their equivalent and find the current that goes through it, that'll be the current leaving the battery. So I would say you could do it the first way of like add up each little bit, but I'm guessing what happened is you didn't get the same answer doing it that way.
Yeah, no, I didn't because I think I see what you're saying now. So the two capacitors right here, they're in series with the capacitor on the bottom,
Yes.
and so those would have the same charge
Yes.
on
Yeah.
both of
Yeah.
them.
Okay. I think I see where you're coming from now too. So whatever charge we get on these, an equal amount is pushed off of them, and that's where the charge on this capacitor comes from. So it's technically not coming directly from the battery. All that is what's on these two capacitors. So if you added up their total charge, you should get the battery charge.
That makes a lot of sense. Okay, thank you so
Yeah.
much.
That's a good question because I mean I was not seeing that instantly either, but that is a valid way to do it. It's just because of that little caveat of like how the charge got there, you have to be more careful doing it that way. Okay, other questions?
Could you do number 26?
26. Yeah, let me jump over to the blank one so I'm not just cheating off myself. So we've got a beam with 5 types of ions, and it looks like the difference is mass and charge of each. They enter a region that contains a uniform magnetic field. The field is perpendicular to the plane. They all travel with the same speed. Okay, so what is the direction of the magnetic field? My first thought for that is, depending on whether I've got positive or negative charge, it'll go a different way in the same magnetic field. I see that I've got 3 positive charges and 2 negative charges. I also notice that 3 charges, or 3 ions, I guess I should say, go to the left and 3 go to the right. So that must mean that positive charge is going to the left in this magnetic field, and negative charge is going to the right. All right, now I think about what would make something go to the left like that. Well, if I've got something going in a circular path, it must be feeling a centripetal or center-seeking force. And so, positive charge is feeling a force to the left when it enters this region. Or by the time it's up here, it would feel it that way. Or by the time it's over here, it feels it that way. So, I can use my right-hand rule, but sort of backwards to infer which way the field, or in other words, my 4 fingers should point to cause my palm to face that way. When the charge first enters this region, its velocity is going to be upward. And so now I've kind of honed in. My thumb should point up, but my palm should be to the left, meaning my palm should be facing left. And the only way I could do that is to imagine dipping my fingers into the page. So we can see how this goes with me trying to draw it. My thumb, like that. My palm has to sort of face that way, and so my fingers all have to... This is the best I can do of pretending they're dipping into the page. And so that's how I infer that the field should be into the page.
How do you know if the velocity is going up?
So when the charge first enters, it's coming upward from here, right? So it's being shot into the box straight upward.
Oh, I see.
But even if I didn't realize that, I could go up here and say, well, at that point, the charge is going to the left, tangent to the circle, but it's feeling a force downward. I can use the right-hand rule with that. My thumb is going to the left, my palm is facing down. The only way that'll work is if my fingers are into the page.
Oh.
Yep.
I see. Thank you.
Could we also look at 19?
Yes. Okay.
Okay, so from the key, I understand what the answer is. So if you want to run that through real quick, you can. But my question was, how exactly does how would you explain C? Like if you had like the compass in person, does that make sense?
Yeah. So if I just went to some place and I guess I'm told or in some way I know there's a magnetic field there. The question is essentially, how do I find that direction with the compass? Is that what you're saying?
Yeah, I think so.
Okay. So, yeah, I walk into a room. This is like a top-down view of the room, and I want to map out the magnetic field. Well, I hold my compass, and if I find that, so the red part will be the North Pole of the compass, and then the black will be the South Pole. If I stand in that spot and see that the compass is pointing that way, the magnetic field points that way, in the direction of the North Pole of the compass. If I go somewhere else in the room and suddenly find that now the compass is pointing this way, now I would say, okay, in this spot, the magnetic field is pointing this way. So that's what I mean of indicated by the North Pole of the compass.
Uh, so could you explain, like, this might be a little far out there, but how does it work for the Earth then? I that might not be the same, but like,
It is. So for the Earth, let's say, so that's what the compass is naturally aligning with, why it always points north. It's naturally aligning with the Earth's magnetic field until we put it into some stronger magnetic field that just totally washes out the Earth's. So if we got those field lines, and this is like the equator, if you're standing there, you pull out your compass, it will point this way. So the North Pole of the compass is in the direction of the magnetic field of the Earth, but that doesn't mean that up here is the North Magnetic Pole, because we think about field lines, they point away from the North Pole towards the South Pole. So the Earth's North Pole is actually this side, and up here is the South Pole. Um, One more bit of information that maybe helps clear it up is you're actually not reading the entire magnetic field direction from a compass. You're reading the component of it that is tangent to Earth's surface. Because if you have a field line, let me make these a little less dramatic so maybe you can see something like that. If you go stand over here, then technically the Earth's magnetic field actually points out this way. But you, being someone living on Earth, you're going to be holding a compass and it's oriented in sort of this plane, right? Tangent to the Earth's surface. So you're actually only getting that little component of the Earth's magnetic field by looking at a compass. The rest of it, this vertical component, the compass doesn't tell you unless you turn the compass 90 degrees, face it kind of perpendicular to the Earth's surface. I don't know if that made things worse or better.
no, that definitely made things better. I keep on forgetting that like the north points to the south. It acts kind of like a dipole in that way.
Yes,
So
yeah.
it
So
makes
think of
sense that it's like
it's
it's pointing towards its south because
mm-hmm.
that's where the okay.
Yep.
Okay.
Yep. So unlike poles attract, but this is still how a compass is indicating the direction of the magnetic field.
It makes a lot of sense. Thank you.
Mm-hmm. That's a good question.
Could you do 42?
42. All right, so we have 3 arcs, either half or quarter circles, and radial lengths. Rank them according to the magnitude of the magnetic field, least to greatest. So I need to make sure I remember that. All right, so to me, this is saying a couple things. For direction, I'm using the second right-hand rule because I want to find the magnetic field they produce. Um, that is an easy thing to mix up, is which right-hand rule you should be using. If you want to find the force on something or the magnetic field something is sitting in, these are both things that the object itself does not control. That's the first right-hand rule. The second right-hand rule is when you want to find the field created by something, something it is making. That's the second right-hand rule. So for this, we want the magnitudes of the magnetic fields these rings or arcs produce. So I know second right-hand rule. Now I can start thinking about the direction for each. But the next thing I would notice is even if I know the directions of the fields for each little segment, I'm gonna maybe need to think about how strong those fields are, because I may have like two fields point in the same direction for this one and for this one. I don't actually know that. I haven't thought about it just yet. But if that's the case, I'm going to have to be able to whittle down a little bit more by comparing field strengths. So for that, it will be helpful to know that smaller arcs mean weaker fields. So for instance, a 90-degree arc, even if it were the exact same size as a 180-degree arc, it's going to produce a weaker field because it's less of a segment of wire for current to flow through to produce a field. And then the other one is smaller radius is going to lead to a stronger field, because then every segment of wire is closer to that point C. And so you don't have that attenuation with distance that you see with magnetic fields. Okay, now I'm going to start looking at direction. So if we have, it doesn't say which way current flows, so I'm going to assume a direction. Say it flows that way for all three. It doesn't matter because say the current was the other way, well, every magnetic field vector would flip, and I would still get the same strength for the net magnetic field. It would just point a different direction. So I'll assume they're all flowing clockwise like that. All right, if I look at this segment in the first one, the second right-hand rule says I'll point my thumb along that and imagine grabbing it and think I get a field that points into the page. So we'll call this BA, I guess, for segment A. And then for the other tiny segment, the current's going to be flowing around it that way. So if I use the right-hand rule for that, I would still get a field dipping into the page. And so those two fields add. We'll call that B, B. And so we're looking at fields add in this case. All right, for case 2, for this segment, it's going to be exactly the same as before, into the page. But now, as I watch how the current flows through the rest of this, it'll flow around that way. And if I do my second right-hand rule, that's actually going to tell me that for this segment, the field points out of the page. And so in this case, the fields subtract from each other. They're pointing in opposite directions. The stronger field would be the one from the green part because it is a smaller radius. And so overall, the field points out of the page for part 2. And then for part 3, we still have into the page for this segment. Then for this segment, it's going to point out of the page because it looks just like half of the thing from part 2. And then current flows like that in the last segment. So if I use the right-hand rule one more time, I'll get out of the page for that. Okay, so it looks like absolute best case scenario where no cancellation occurs is going to be this one. So that's the greatest. I'm expecting 1 to be the greatest. So now it's just comparing 2 and 3. I think this will be easier if I actually sketch out what I'm seeing with these field vectors. If I imagine looking at these from the side, I would see for picture 2 a field poking out of the page that's green and a weaker field going into the page that's blue. For the picture on the far right, I'd see a field poking out of the page that's green but not quite as strong because it's from half a segment. Another field poking out of the page from the red part, but it's even weaker. And then blue, it's the same as before. And so I think I'm getting overall a weaker net field out of this last one compared to this one. So I think that 3 should be the weakest field. And so it would be first in this ranking. I'm going to come back over here. See if I did that right. Yeah. Okay, and it looks like I did a much cleaner version of that in the original solution.
That's the that was the problem even on the homework. I had trouble with after imagining just whole using the second right hand rule with what, because I knew the top portion will have to go in. It was just the bottom portion that kind of
Okay, so knowing whether it sticks in or out?
Yeah.
Okay, so let me try and hone in on that part for a second. So we're looking at current flowing like that versus like that, for instance. Well, in the first picture, my thumb would go this way, grabbing on. Oh, this is going to be a nightmare. Thumb goes like that, and I try to grab onto the loop like that. My fingers will dip in something sort of like that. Just picture it less horrifying. And then for this one, my thumb still grabs on like that, but to grab the loop like that, my fingers actually have to poke up through from the other side of the loop. If y'all looked at the quiz and the solutions and the hands looked okay, it's because it took me like 20 minutes to try and draw those. Um, but that's the difference, is which way your hand is poking through that loop. Does that make sense?
Okay. Yeah, that picture makes sense.
Okay. Again, with this, I would recommend if you have a roll of tape, hold it. Imagine putting your thumb on that roll of tape with your thumb having to go like that, meaning current's going around like that, versus your thumb having to go like that, because current's going around the other way. You have to flip your hand over to do it, and so you'll be able to see which way your fingers are poking through the piece of tape, or the roll of tape.
Oh, I see. Okay. That makes sense. All right. Thank you.
Mm-hmm.
I'm sorry for asking so many questions.
No, it's good.
Could you don't have to do it right now. I just have to leave early. I was wondering if you could do 40 at some point,
Um,
and I'll
yeah,
just watch the stream back and see how you did it.
yeah, I can go ahead and start doing that one.
Okay. Thank you.
Uh-huh. Okay, so the question is the magnitude of the magnetic field at point C if we're given that D is 0.1 meters. So I want to know the field here. I think a trap that's easy to fall into for this is with a setup like this, we've talked about magnetic forces a lot. The force one wire exerts on the other. So the, let's see, it is mu naught L I1 I2 over 2 pi, maybe 4 pi, I forget. That's not what is being looked for here, though. It's looking for the net magnetic field, and so for that, I just do the first part of what I had to do to find out if the wires attract or repel. So, I imagine putting my thumb on the wire in the direction current is flowing. So from this top wire, in order to do that and grab onto the wire, my fingers will do something like these sausage fingers. I'll do something like that to wrap around. Meanwhile, if I had to put my thumb the other way to grab onto the wire, and then I imagine grabbing on, fingers will go something like that. I don't know why it went so much better for this one. But what I end up seeing is that either way, I picture the circle around this thing that results from that. It's the field is circling like that around the wire, or for this one, field is circling like that. For either one at point C, so somewhere in the middle of both, I see the field poking up out of the page at me like my fingers are. So I follow this around, whereas my finger about to go right here, it's about to go out of the page. And I think I can clean this up a little bit by using actual ellipses. It going over the top of the wire like that. This part on the left goes under the wire. It's just if I try and erase that part, it'll erase the whole ellipse. And similar for here, but flipped over. Now the part on the left is what's going over the wire, and the part on the right is going under the wire. So dead center, that's going to be, if I line those up a little better, it's going to be a field poking up out of the page for both of the two, meaning I will add their overall fields. So the net magnetic field is the field from wire 1 plus the field from wire 2. So that's mu naught I1 over 2. I'll just leave it as R1 for now, plus mu naught I2 over 2R2. Oh, I'm forgetting a pi, since these are straight wires. And then I'll look at what I should call R. Well, point C is that distance from wire 1, that distance from wire 2. In either case, it's half of this distance. So my R would be 0.05 meters for both of them. All right, so I have the same R, and then all these other constants. So I'll factor that out. And so it should just be that for mu naught, 2 pi 0.05 meters. I1 is, it looks like 6 amps, also 6 amps for this one. So 6 amps plus 6 amps, and that comes out to whatever it comes out to.
For that same question, how could you tell if it was if for the B net it's adding?
Because they're both pointing out of the page. So for each of these two wires, if I think about which way the magnetic field's going, I'll kind of come back to that on the left-hand side so we can see it. The field is wrapping around that wire like that. And then for the bottom wire, the field is wrapping around like that. So here I've made it a little bit clearer, like where it's dipping under and over. So if I think about which way that means the field is pointing right in the middle, it's going to be coming out of the page at me, no matter which of the two fields I'm looking at, the one up top or the one down bottom. Let's say we took a side view. You were standing on the side of the two wires, so you're sort of looking down the barrel at them. You'd see the top wire coming out of the page at you, the current is, and then the bottom current is going into the page, right? Okay, so now it might be a little bit easier to see how the second right-hand rule comes in. For the top one, if I use that second right-hand rule with my thumb sticking out of the page at me, the field will wrap around like this. The bottom one, if I do the same thing, now my thumb is sticking into the page. In order for my thumb to stick into the page, my fingers wrap around the other way. I look at which way the field from each one is pointing. I call this wire 1, wire 2. The field from wire 1, I follow around and around and around and around. When I get right here, which way am I about to go?
Out to the right.
To the right, yeah. Okay, so I've determined that for wire 1, the field points to the right. Okay, I do the same thing with wire 2. Go around and around and around, and when I'm here, which way is my pin about to go?
To the right.
To the right. So that field also points to the right from this perspective. So they point in the same direction the fields add. If I come back to the original perspective, that would be the field sticking out of the page at me.
I see. Okay. Thank you.
All right, well, if anyone does have further questions, feel free to email, and I'll get back to you as soon as I can. This weekend will mostly be grading other exams and getting y'all's ready. So if it takes me a little bit to get back on emails, that's why, but I will try to stay on top of them. All right, y'all enjoy your weekend.